In this session, we're going to look at a few alternative ways of implementing coherence. We already know that the cache line state plays a very important role when you implement cache coherence. We looked at a protocol that had 4 states. That protocol had the state modified, so here we just redefine it again as we talked about it before. But there are many other states as well that you can think of when you implement cache coherence protocol. Another common state is the state exclusive. State exclusive means that the cache has a clean copy in its cache, and it's the only cached copy. So compared with the state modified, the difference here is that it's a clean copy, which means we don't have any obligations to perform a write back when we replace this cache line from the cache. Other possible states we've already looked at: owner state, the shared state, and invalid state. There are, of course, many other options than this, but these are the 5 most commonly used states when we implement the cache coherence protocol. So once more, highlight the new friend of ours, the exclusive state, saying that this cache has the only cache copy, but as this copy has not been modified yet, so it's still clean and it's still identical to the copy that resides in memory. So when you design a cache coherence protocol, you first decide which of these states should be represented in the cache coherence protocol. The first protocol we looked at was the MOSI protocol, because we had the 4 states M, O, S, and I. One signum of that protocol is that that protocol leaves one dirty copy in a cache when we perform a cache-to-cache transfer. Going back to our example, when the middle cache that had a dirty copy in state modified saw a read request from the left cache, it sent over a cache-to-cache transfer and went to the owner state, just to remember itself that eventually upon replacement it had to perform the write back. You can also design a protocol with fewer cache states, like the MSI protocol. You have the state modified, shared, and invalid. Compared with the MOSI protocol, the signum here is when you perform a cache-to-cache transfer, you will also need to update the memory, because there is no state owned where you can remember that eventually upon eviction you have to update memory. Instead, when you perform the cache-to-cache transfer, when the middle cache sends data to the left cache, it also will have to update the memory to perform a write back. It's still okay for the middle cache to hold on to the data, the cache line it just modified in its cache, but then it has to go to state shared because we have no owner state. You can also imagine designing cache coherence protocols with more states. So the MOSI protocol, we have added this new friend of ours, the E state. And the signum of this protocol compared with the MOSI protocol is that the first time a cache reads a cache line from memory, it will go to the E state. So the E state saying this is clean, but it's still the only cache copy in the system. If that same cache later on needs to become a writer, and no other caches have read that data up until that point in time, it's still in the E state, then it can very cheaply transfer from the E state to the M state and become the writer without having to broadcast its intention on the bus. Let's look at a fairly simple example, and even though this is a simple example, I have to reveal that I actually lost a beer on a bet on this example, and later on I'm going to tell you exactly how. So if we going to execute the code a equals a plus 1, you can imagine that the kind of assembly code that's going to be generated is that you're going to have some kind of load from memory location A into some register. You're going to have some add instruction that adds 1 to whatever register you just decided to store the value A in. And at the end of the day, you're going to have to store the result back. So you have to store the result to A somehow. So when you perform these 3 instructions in the CPU, for the first instruction, assuming now that initially A only resides in memory, On the MOSI protocol, you would generate the read to share request. Uh, uh, Upon the load will generate the read to share request, and after that read to share request on the bus, you will be in state shared. The add instruction, of course, is not going to generate any kind of coherence activity or memory references to the cache at all. So from the coherence perspective, that's a fairly uninteresting one. And then the store instruction will have to invalidate, send out an invalidate on the bus, even though we know that there may not be any other cache copies out there. This MOSI protocol dictates that we will have to send out the invalidate request in order to state modify. If we have the MOSI protocol, on the other hand, the MOSI protocol for the first load that's performed would also send the read to share request on the bus. And somehow the coherence protocol would notice that that there aren't any other caches in the system that has a cached copy of E. So how could that be done? Well, for example, if all the snooping caches that feel that they have a shared copy of this cache line, but still they are not entitled to make the reply, they can still raise their hand somehow, signal to the cache coherence protocol, watch out, I have a shared copy. And when you implement the MOSI protocol, if you, at the time that your read to share request is sent on the bus, can see that no other caches raise their hand, say I have a shared copy, then you put the cache line in state E. Add is performed, and later on when you will have to perform the store operation, if you are still in state E at that point in time, which means you have not seen any other caches requesting a copy from this cache line, then you would simply go to state M without having to broadcast any information on the bus. Seems like this is a very simple example, and it seems that this could not be all that important for a real computation, and that's what I thought as well. I bet a friend of mine that implementing MOSI protocol was a stupid idea because you would never really be able to see any performance benefits. Well, within an hour, he had showed me that one of the most important workloads that we were running in some microsystems at that point actually ran 30% faster using MOSI protocol than the MOSI protocol. And that workload was a hardware simulator. And hardware simulator is perform a quite simple task. They have an enormous state that represents the design that's going to be simulated, and they go through each node in that design to read what the previous state is, to figure out what the next state is going to be, and then write that state back. So it's very much like reading the old state, figuring out some stuff, and writing the new state back to each of those nodes in the state representation. So these kind of things would be performed many times. And as you can see on the left-hand side, you're going to generate so many more coherence transactions on the bus. And if the Snoop bandwidth is your limitation in the system, then you're going to run substantially slower using the MOSI protocol than the MOSI protocol. Another option we're going to look at is something called an update-based protocol. In this example, it's an update-based MOSI protocol. So remember that when we looked at the MOSI protocol before, we said it was an invalidation-based protocol, and here is its counterpart. So a different strategy for you when you would like to create the coherence on the write request from the middle cache would be, instead of invalidating all those other copies, what you could do is simply update them. And we have a broadcast media, we have the broadcast bus. So instead of sending an invalidation request on this bus, you can send an update request on that bus, saying, anybody out there who has this cache line, please put in this new and exciting value in its place. So now all of them are updated. So we have 3 copies of this cache line. And when the next read request comes along, we don't no longer going to generate the cache miss. We're actually going to get the cache hit, and we will completely remove the need to do that, make that cache-to-cache transfer. So that seems like a fairly good idea to avoid some cache misses caused by coherence. However, upon the next write of the same processor, we'll have to repeat the whole process once more. Even if no other threads in any other any other threads needs to read that piece of data between those two writes, we still have to keep updating the whole world every time we perform writes, and we easily become one of those nasty Facebook friends once more. So update-based coherence, it's when you write a new value to the other caches instead of validating it. It is good because it can avoid some coherence misses, but it can consume a huge amount of extra snoop bandwidth, since you repeatedly will have to send out write requests, even if none of the other caches really are interested in your message. It also is from an implementation point of view, is quite hard to implement both actually coherence as well as memory models using that kind of broadcast updates, even though it has been implemented a couple of times in commercial systems in the 80s and 90s, and as far as I know, 2 systems implemented update-based coherence. One was SparkCenter 2000, beginning of the 90s, and its predecessor that was made by Xerox Dragon, also had that. So often, update-based protocols are referred to as the Dragon protocol. What I'll do now is just quickly go through an exercise we're going to have next time we have in real-life lectures. I'm going to tell you what kind of problems we're going to work on and what kind of questions I want you to just mentally prepare before you come to that lecture. We're going to look at a real execution that's performed by 3 different CPUs. We assume it's going to be MOSI protocol, and we assume that all processors are going to execute the same code. So this first is a while statement, which seems to be an infinite loop. If the value of A doesn't have some sort of magic value, then we do a couple of updates, and then we have another infinite loop while A is no longer equal to 4, we sort of stand. But we also have to read the fine print here to figure out how we should perform this execution. So initially, we assume that CPU 1 it's going to have its value for my ID is going to be 1. So you can look at my ID. So this is like a register, and CPU 1 happens to have a 1 stored in that register, while CPU 2 has a 2 stored in that register, and CPU 3 has a 3 stored in that register. We also state that the global variables, the global shared variables, memory variables we're going to deal with are A, which is initially equal to 1, and B, which is initially equal to 0, and they both reside in memory only initially. Then we're going to assume some kind of interleaving or execution. We're going to assume that we're going to look at execution, have the CPUs take execution steps one by one, so we more easily can figure out what's happening. So we're going to assume that CPU 3 makes it first a memory operation, load or store, and then CPU 2 makes its first memory operation, load or store, and then 1. And then they're going to keep repeating this over and over again. So you're going to get some well-defined interleaving of the execution. We are going to execute this code sort of on paper and then fill out a form like this. We're going to tell for each of these execution steps, CPU 1 performs the load, CPU 2 performs the load, CPU 3 performs the load. For each of these steps, we're going to tell what kind of bus transaction are going to be sent on the Snoopy bus, if any. And we're going to tell what state changes we're going to see in the cache of each processor. So here we have CPU 3's cache. We have the value A and the value B. Initially, they are both in state invalid. And here's we're going to see state change. We're going to see that the state of A goes to state shared, and the value it holds is the value 1. We're also going to note which device will reply with data. So when you send a read to share request here, the first thing that happens, the memory will reply with the data. And then so on, we go to CPU 2 and CPU 1, and then we go to CPU 3 again. So note very well here that CPU 3 in this situation doesn't send any bus transaction. Why? Well, because we got the cache hit. Because A is still in state shared here because there has been no changes. still a state shared and the value is still 1 at this point in time. Going back to the previous picture. So what will this execution really do? Well, we have this, what I call the infinite loop in the beginning here, while A is not equal to my ID. And so CPU 3 will perform a load operation first. It will load this, the value of A, otherwise it cannot perform this test. And it will see if this equality holds here is A is not equal to my ID, and CPU 3's my ID is 3, and A's value is 1. So clearly it doesn't hold, so it will have to stay in the infinite loop. Same thing holds for CPU 2. It's going to perform the load operation. It's going to get the sad news that no, A is not equal to my ID. And then comes our hero CPU 1 along. It performs the load operation, loads the value A equals 1 from memory, makes test to see if my ID is equal. It's not equal to that value, and if the this test doesn't hold, that means that CPU1 will fall out of this infinite loop even before it started, and it will go down and perform these operations. It will update B, and then it will increment the value of A. Incrementing the value of A will make CPU2 really happy, because it's now been standing in this infinite loop for a long time, waiting to see exactly the value 2. So now CPU2 will keep working here. Meanwhile, CPU1 will get stuck in this infinite loop over here. And it will be stuck here up until the point in time CPU3 comes along and changes the value of A from 3 to 4. And then it will fall out of this loop. Right here. So this is the kind of exercise we'll do. And as usual, I will explain one example on the board, and then you will have to work on these kind of exercises.